Welcome to the last main lecture of our series in Perspectives in Paleontology. Next week, the home team will have a chance to perform in a series of short sketches by members of this faculty. That meeting will be in the same room, same hour, but next Thursday afternoon at 3:30. The community structure of fossil organisms is one of the potentially most fruitful and yet most neglected of paleontological activities. Yet from such studies can come new insights to form, habit, and habitat, and new light on such things as the evolution of adaptation, the origin of major groups of fossils, and related details. A conspicuous exception to the generalization that community studies are neglected in paleontology is the work of Professor Everett C. Olson, who will speak to us this afternoon on community structure and the evolution of the mammals. Professor Olson is a leading student of the early tetrapods, particularly the fascinating reptilian-mammalian transition. For a long time, there was a great gap in the evolution from pelycosaurs to the more advanced therapsids in the early evolution of the mammal-like reptiles. The later phases of this evolution were represented in South Africa and Russia, and the early stages were represented in the earlier Permian of the United States, but there was nothing in between. Rocks of intermediate age, nevertheless, were present in Texas, but were reputed on the word of people who had examined them carefully to be barren of fossils. Professor Olson was not to be deterred by such faint hearts, but turned his vigorous attention to examination and exploration of these beds in search for the missing elements. Season after season he pursued this search until finally the beds supposed to be barren proved to be fruitful, and eventually he obtained a nearly complete transition from the early primitive pelycosaurs into the more advanced therapsid type of reptile. It is this evolution that he will tell us about this afternoon. Professor Olson has spent, with the exception of field work in Texas and a long visit in Russia, all of his professional career in the service of the University of Chicago, where he is the chairman of the Committee on Paleozoology and professor, I believe, of geophysics. Professor Everett C. Olson.
Thank you very much, particularly for the credit for my geophysical background and associates. I was going to explain myself to you a bit before, and I think it now is very necessary that I do, because my brand of geophysics is rather an unusual one, and I became such because the department which I belonged to, that was the Department of Geology, merged with the Department of Meteorology, and for reasons both practical and financial called itself Department of Geophysical Sciences, being a very popular term then, and it's still quite popular. It does bring money. I, however, am a vertebrate paleontologist, which is a far cry from that, and to some degree this makes me a bit different from the other speakers that you have had here. As a matter of fact, some people think vertebrate paleontologists are quite different. Anne Rowe Simpson analyzed a great many people, as you know, by groups by Rorschach tests. She did the vertebrate paleontologist because her husband, George Simpson, was a member, and she thought she ought to find out about his group. And she found there was one other group that rated higher in the numerical scale, and that was the artists. So we have had a reputation of being a little on the unstable side from time to time. This, I maintain, is just because we're misunderstood. I don't think it is really a characteristic which puts us there. It's just that we operate in a slightly different frame of reference than some others do. My own frame of reference is basically that of biology, although I was trained as a geologist primarily. And it is primarily dealing with the origin of higher categories or the origin of higher levels of organization as contrasted to processes of radiation evolution. And this more or less stems out of my heritage of the heyday, as I would think of it, of evolutionary study as far as paleontology is concerned, in which the vertebrate paleontologists were very intimately concerned, paleobotanists to a degree as well, and the invertebrate paleontologists much less. This was the time which had stretched roughly from about 1935 to 1955, when a tremendous interest in the integration of the various aspects of study of evolution came about under the aegis of such persons as your first speaker, Ernst Mayr, George Gaylord Simpson, in the botany, particularly G. Ledyard Stebbins, and many others, of course Julian Huxley being very important in it. This was a time when paleontologists outdid themselves, and this was the time, incidentally, the Rorschach tests were taken. It might have had something to do with it. We went pretty wild, I think. We began to feel that from the paleontological record we could come up with great evolutionary truths, and we did come up with what were supposed to be great evolutionary truths. We became quantitative. We applied mathematics. And then, although a great deal of good came from this, I don't think there's any question of it, and the current theory of evolution had strong impact from paleontology and many other places, a great disillusionment set in. Most of my colleagues, not all, but most, abandoned the evolutionary motif in their work and went back to describing and saying, well, we can do history, but that's all we can do. Now, that's not in any sense derogatory of the job of paleontology of reconstructing history, which is important, which is one of its main functions. The naive positivism of this era, however, went. I have a heritage in that, and I did not follow in the crowd and throw out evolution at that time as a thing that could be studied, but felt perhaps we could go into it from other places. I think one of the reasons this thing went bad is that there was a disillusionment because nobody paid much attention to what the problems were. In other words, nobody really went into an analysis of what paleontology could and could not do in evolutionary studies. As I see it now, the evolutionary theory, by that I mean the synthetic theory, the neo-Darwinian theory, the selection theory, whatever you wish to call it, has a distinct role in paleontology in this sense that it is the only theory that brings those things we read in the fossil record into accord with life processes as we know them today. If we don't do this, we have no legitimate basis for biological study at all in the fossil record. I don't think, on the other hand, that the study of fossils per se can contribute to an intimate knowledge of the processes involved. In other words, I think this is where the difficulty came in that period. We were trying to do this and it was impossible. I think it's logically impossible. Put in another sense, I think that the evolutionary theory is very necessary to interpreting the fossil record if we're going to follow this matter of bringing it into the life processes as we know them. I'm not sure, however, and I have some hesitation on this, whether or not it is sufficient, whether it is a sufficient vehicle within which we can view the record. By that, I am not sure that what we get from studying modern life processes is totally sufficient to explain all that we see in the past. I don't mean that you can't explain it all. You can. We can weasel our way this way and that and get it in. But sometimes the weaseling becomes so extensive that you wonder. I just expressed this doubt, and now having expressed this doubt, I'm talking completely within the framework of standard orthodox evolutionary theory from here on out and dismissing the doubts. I'm assuming then, as an operational basis, this is the thing we must work with, and that's what we're going to do. Now to the more substantive part of what I want to talk about. Just what is it in this origin of mammal problem that we're dealing with, and where do communities get into it? Well, first let me get down very briefly to the record. Professor Cloud mentioned the record comes basically from 3 places in the world. It starts in North America. Now, in the very early part, in the Carboniferous, when we first get something we can work with, and I'll explain why we start there in a moment, this is basically North American, but also European to a degree. In other words, in the late Carboniferous, there isn't too much to choose on. As a matter of fact, there isn't very much evidence. And what we do get is a bit widespread. When we come into the Permian, however, where this record first becomes clear, then we're definitely in North America and not much of anywhere else. And in North America, we're in Texas and Oklahoma, in New Mexico, and branching out from there into Colorado, adjacent areas, and also in the eastern part of the country to some extent. Then things end here. Now, my good Professor Romer, as was pointed out earlier, said things end here. And we were able to go up a bit higher. Now I say things end here, up here, and I hope somebody can come along and make a liar out of me and can find things higher in the record. I haven't been able to. At the moment I was talking to Dr. Vaughan, he hasn't been able to. We're the principal 2 people who are trying to. Maybe one of us succeed. But we have to go to Russia. In the Soviet Union, in the pre-Uralian area, there are beautiful fossil deposits. Well, they're beautiful to me. They're old, ugly red beds, as a matter of fact, but they're quite pretty if you like that sort of thing. You can find fossils, and the fossils are very nice. They go up a ways, and then this sort of peters out. It does go on, but it isn't very useful. And then the scene transfers to South Africa, where the immense amount of material from the Karoo Basin carries the record on further up into the late part of the Triassic. And then for reasons which are those of the vagaries of sampling, I presume, suddenly all over the world in different places we get a record of this thing. China, South Africa, North America, England, and so forth, we find this story continued. The reason I wanted to make a point of this record is that one thing that really worries me about any interpretations I make or other people make is the problem of sampling. What is the adequacy of our sampling of the fossil record? Now, when I'm working in the Texas or Oklahoma Permian, I feel like this is the world. But was the world like this? The little evidence we have suggests that it was pretty much like this. But how widespread this was, I don't know. How much sampling error we had is a serious problem. We'll take it up more later. The record then begins in the Middle Carboniferous. Why? There, for the first time, we find a stock of reptiles that seems to show some evidence of having some characteristics suggesting that from this stock may have come the group of reptiles we call mammal-like reptiles. Where do we end this origin of the mammals? That's a good point. The origin of the mammals presumably ends when the first mammal came into being. However, if you can define when this is, you're better than I am. Matter of fact, if you can define where we may draw a limit between reptiles and mammals, you're doing something I'm unable to do. So I say this story we're talking about continues up into the Cretaceous, although you'll find in the books the mammals came into being in the late Triassic or early Jurassic. The reason for this is that the flowering, the radiation of mammals to produce the stocks that we know today, the placentals and the marsupials, was a Cretaceous phenomenon, and it began probably in the late Cretaceous. Till that time, we'd had something of a gestation period, when we had things that were sort of mammals, but apparently they were not entirely mammals. So this is the limit of the story. Middle Carboniferous, middle upper Carboniferous at the base, the Cretaceous at the top, and the story is in between there. The point of all this is that a higher category, such as the class Mammalia, did not come into being quickly. It came into being only over this very long period of time. It came into being and can be understood, I think, only if we understand all that went on with it. The physical changes, but more importantly, the changes in the associated biota, the fish, the amphibians, the reptiles that were evolving toward mammals, and of course the plants. This is a big order. I think not only that, but we must also understand the invertebrates that were associated, these being freshwater terrestrial invertebrates largely. And furthermore, we should of course understand the interaction between these various groups if we're going to get to the whole picture. Well, I will bravely later on try to give you this whole picture of what everything was doing at the time. For the moment, in order to give you a little better picture of what's involved, let me stick to a phyletic approach and deal specifically for a few moments with these animals that began as not mammals and ended up as mammals. Or I like to put it in the basis, and it's a very crude one and obviously absurd, but it's functional, that there is an animal in this line which is 0% mammalian, and that when you reach a mammalian level, it's 100% mammal, obviously, and that we can sort of speak in terms of percentages along up the line. I realize that I run into much the same problem here as the numerical taxonomist will do. Depends on how I weight or refuse to weight my characters as to how I get a percentage rating, but it makes a certain amount of sense. If a thing isn't at all mammalian, then it's 0. How do we know it belongs on the line? Well, maybe it's 0.05 then or something of that sort. We just get it in. If it is all mammal, it's 100%. But when it's all mammal, you'll get an argument on it. So, of course, we're only dealing with hard parts here. We'd like to know about some other things. If we did, I'm convinced we'd be only more confused rather than less, because we'd be getting now into the problem of what constitutes warm-bloodedness, what constitutes a certain heart condition, when is hair hair, and how much you have to have any hair, and so forth and so on. These would all be problems. Fortunately, we only have to deal with these as far as bones are concerned. And we have to deal with such problems as, are you a mammal when you have only one element in the lower jaw, if you aren't a bird, which of course does the same thing sometimes. This sort of thing. I mean, I'm just making this humorous because we can't classify this well, and my 100% to 0 falls within this absurdity, but nevertheless it's very useful. The phyletic approach brings us to two key groups that are important, and I guess I will put them on the board because I'm going to speak of them. My printing is bad, perhaps you can read it. One is what I will call the Captorhinomorph. And the other is what the one I'll call the synapsids. You all know these terms, I presume. If you don't, I'll have them up for reference. Under which we have pelycosaurs and therapsids. And these are mainly the terms we'll be using. Trust that's our and not a commentary here. These are what we're going to use. You may wonder where, if you're somewhat acquainted with terminology, the catylosaurs are. As far as I'm concerned, the catylosaurs aren't. There is no such thing. This is a misnomer. It doesn't mean anything. It is applied to 3 very distinct groups. Putting them together doesn't make any sense. Furthermore, as conceived, it didn't mean at all stem reptile in the sense that we think of stem reptile. It meant a particular reptile in which it lost its ex-occipitals, and the base occipital protruded out back, and it was called a stem reptile for that reason. So that, let's get rid of catylosaur if you're used to using it. I don't use it because I don't like the term. I don't think it means anything. I think it's confusing. Captorhinomorphs are these very early, rather lizard-like in general structure, reptiles that show certain characteristics which I won't specify that suggest that from them came this group which is known as the mammal-like reptiles. They began in mid-Pennsylvania, as far as we know them. They persisted up through somewhere into the middle part of the Permian. Something of that sort, their range. If we could draw a line like this then for their phyletic pattern and just label that C, we'd find they have some sort of relationship to the others, which we can call the mammal-like reptiles or the synapsids. And these had a dual radiation, something like this. And I won't draw the arrows completely across, I'm not too sure how to go, but another one up in here. And these are the pelycosaurs, and these are the therapsids. And this is about beginning of the Permian. This is the middle part of the Permian. This is the upper part of the Permian, the Triassic. And this just shows you how the thing goes. These are then the groups we're talking about. These then, if we take it on the scale, we have a 0% mammal down here. And somewhere up in here, we would have something that would be about 95% mammal. In other words, I would say then most of the characteristics of this organism are those that we call mammalian. Now, of course, there was no mammal at this time to be 95% of, but it approached this thing that we, in retrospect, call it, so that we'll think of it in that sense. This always bothers me, any time it bothers me. You call these things mammal-like reptiles, and of course, they are now, but they weren't then. What do we see in this phylogeny? Well, one thing we see is what I think has to be called, no matter what you do with it, progressive change. We see, now progress, of course, is a bad word, but how you can have evolution that doesn't involve progress in one fashion or another, I'm sure I don't know. Maybe you can call it development if you wish. But it is a progressive change through time, and this progressive change in this line leads towards the condition that eventually is mammalian. In other words, there is a gradual and continuing acquisition of many features that eventually become consolidated into the class Mammalia and are basic to its radiation. During this time, of course, rates differ very much. And I think I'll turn over now to slides and point out a few of these things on the slides to you. I'm sure that there's a great difference in the degree of acquaintanceship with these animals, so let me show just a few of them to you. This is a typical carnivorous pelycosaur. Where is he on the mammal scale? Well, he's about 15% or something of that sort, I should say, based upon certain structures of his cranium in particular, certain differentials in the teeth, certain patterns of the limb bones and such. These are two of the same thing. This is a New Mexico specimen. Very similar to him from Texas is a long-spined or fin lizard called Dimetrodon. The next slide, please. And way up the scale, having progressed far towards mammals, and perhaps being at, say, an 80% level or something of that sort, is this particular mammal-like reptile from South Africa, shown in the skeleton here, which looks quite like a mammal. There's some things I could point out. First of all, it has a differential ribbed basket and lumbar region. We may infer perhaps some diaphragm developed in here. We may infer quite incorrectly, but it's not impossible. It has a pattern of toes which are mammal-like in their formula. Many features of the skull are mammal-like. It has a lower jaw with largely a dentary. The brain is somewhat enlarged. The dentition is well differentiated. It has a secondary palate. You could name many things that are found later in mammals, which are in this reptile, which is quite a reasonably direct descendant from the first one we saw as far as the record goes. The next, please. Remember, we're looking at this purely phyletically at the moment. Lower jaws are always brought into the picture. It's extremely important. When I speak of progressive change, I speak of the change that went from this complex type jaw with many elements through these, where the dentary keeps increasing, through these, to where the dentary becomes almost all, and down the line, I hope I'm going in the right direction. You can't see these very well. And you notice little elements back here, to a stage where we reach a mammalian condition, in that the dentary forms an articulation, but we retain a reptilian condition in that the articular is still in there. And this is a pretty terrible thing, because this is where the definition of mammals and reptiles is supposed to go, when it goes into this sort of articulation, and one comes in, the other goes out. Well, they don't do this. They're both in at the same time, so who is he? By definition, he's neither one nor the other. He's in between. Finally, down to an essentially mammalian condition here. I said there's a lot of difference in the rates of evolution here, and this is true. We get very little radiation to this point in the pelycosaurs towards mammals. We get a slow development up to here, then a very rapid shift, then a stabilization with a very slow shift from here. These rates are very different. Another thing that turns out, may we have the next slide, please, is that, well, I forgot, it's coming on. This is another example of things that happen. This is the alisphenoid bone with the epipterygoid showing progressive change from a reptilian condition through here, still a reptilian condition down here, over into a typically mammalian condition down in here. I've forgotten this one came in here. The next, please. I will show some other things I was going to speak of before. Yeah. I was going to say, when I got interrupted by that particular slide, that in this progressive evolution, very interesting thing shows up. I think it's important. The evolution of a progressive sort that I've mentioned, through stage like that, to this, to that one, down to here, and down to here, and then we stop, is one that goes through a carnivorous line. These were flesh eaters. What kind of flesh they ate? Well, there's a lot of questions we can raise, and I'll take some up as we go along. But nevertheless, they were good flesh eaters. These are herbivores. The herbivores sprang up sporadically, but having sprung up sporadically, they died out and did not generally give rise to later groups, so they were continually coming off one place or another. Next slide, please. Finally, just to show that there is a great deal of detail possible in this matter of evaluating mammalness, these are some brain casts, cranial cavity casts, which I made out of serial sections, showing some of the detail that can be obtained, and showing that such things as the evolution of the floccular area, some of the basal structure of the brain, and so forth can be worked out. I believe that's the last of that slide series, isn't it? Well, these are changes then that we see, and in this phyletic pattern we also see a number of other things. One of the most impressive is that as this goes towards mammalness, various lines go towards mammalness, there is a tremendous parallelism. The reason I'm setting these things up, these are matters we have to explain if we're going to explain this origin of mammals. In a phyletic sense, we see that. Another thing, of course, is evident. The transition is very gradual. There are no jumps. There are no saltations. This fits beautifully with the idea of accumulation of characters and production of mammals. And that's best brought out, perhaps, in ear structures, which we certainly don't have time to go into, but which do show this transition very nicely. There's one other interesting thing, and I should mention here, which isn't quite in the context. Mammals have many characters which are like those of amphibians. Many characters which are very hard to conceive in terms of a reptilian origin, such as a lizard or an alligator. In other words, they aren't like this. They have soft skins, they have glandular skins, they have hair, they have certain kidney characteristics. They have many characteristics that are reminiscent of amphibians. It's a thought to keep in mind as we go along. Well, all of these things are interesting. Some explanations are possible on a phyletic approach, but I at least found myself quite frustrated with this and began to go into the thing that's the title of this talk, and that is the community approach. Whenever I talk about my communities to ecologists, they shudder. The paper I did on this, I sent into Ecology. There is a paper, somebody's read it. And it came back with several comments. First of all, this is very interesting. We sympathize with what you're doing, but what's your evidence? Please explain it. And what do you mean by community? One chap that read it said, I don't know, maybe he's here for all I know. He said, I like what you're doing. He said, but I have read this and reread it, and I have no idea what you mean by a community. Well, I read the paper over after it came back, and I was as confused as he was. I also found that I hadn't detailed at all what I meant, and then began to examine to see what I did mean, and found out that I had some thoughts in mind after all, and I think the paper as it came out here first in a carbon copy and then in a galley proof, which has been with me for about a year. I think the paper will be out sometime. Ecology is fairly slow, as some of you probably know. I think it makes some sense. Well, what is this community I'm talking about? Well, of course, if you go to something like Hesse, Lee, Park, and Schmidt, you come up with a definition. If you go to some other ecology thing, you come up with another definition. As a matter of fact, there are almost as many definitions as there are community ecologists, as far as I can find out. Now, where do I fit in this pattern? Well, first of all, I'm not an ecologist, so I have more freedom in defining my communities. I am at the upper end of the spectrum. There is the ecologist who will speak of the community of a drop of water, for example, something of that sort. I'm at the other end. This is the biggest sort of community you can think of. This involves all of the vertebrates, all of the invertebrates, all of the plants that exist in a structure which is limited primarily by some consistency of interaction of its elements. Now, there are such things. They're big. You can think of them, perhaps, and they're used in ecology sometimes. This is the sort of thing I'm thinking of. It's the very broadest. And it's not only the elements that exist there, but more importantly, it is the coherence of the structure and the nature of the interactions that are involved. This is one thing. Secondly, this community, as I'm thinking of it, has persistence in time. It does exist through time. It has temporal. Now, anyone does, of course. You speak of a community, well, it's here today, and it's here tomorrow, it's here next day. But I mean in terms of thousands of years, hundreds of thousands of years, a million years. There is this geological time persistence. The first time I came up with this, and eventually you've seen this paper, it'll give you the idea. I was working with a fauna which I called a chronofauna. It was a paper I gave actually out in Berkeley back in 1951 or 2, I think, quite a long time ago. But I've just been fussing with this idea ever since. It's a fauna which has structure through time. Now, in the community, as in this particular fauna, the elements may change over time. In other words, we may not always have the same species. Genera may be replaced by other genera, but the basic structural pattern of interaction, that interaction is of many sorts, but the most obvious one is the feeding interaction, persists. Now, you can see right now I'm in trouble. There's two communities have been defined here. One is something that exists at a time. The other is a conceptual structure into which you can plug all sorts of things, but in terms of the structure it persists and may be anywhere in space or time. It's no different from species, of course. A species here and now has certain individuals. A species over time has other individuals which are operating in precisely the same fashion as their ancestors, or nearly so. So there's the substantive community that exists at any one time. There is the conceptual community, and it's the second I'm speaking of most of the time. When the final picture gets on the board, you will see, however, specific examples of the conceptual types as they are plugged into the fossil record, or as we've dug them out and conceived them there. Well, now how much can you do with this whole thing? What's the evidence, as the critics say? Well, that's an almost impossible thing to tell you. It is the evidence that comes as one walks in the field day after day, week after week, year after year, digs up a little fossil here and a little fossil there, and finds an assemblage here in a particular kind of rock here, which is related to a particular rock there, which in time is slightly different, and which eventually appears in two forms, one in reams of field notes, and the other is in an idea in your head which you can't really put down on paper as such as precise evidence. This is where it comes from. Now, the evidence that is published is the rationalization of this. In other words, we then can turn down and put on paper, at such and such a place I saw such and such, such and such, such and such, and this is it. But it's 1,000 of those things that produces the evidence. It's difficult. Now, can communities evolve? This is the other question that must be asked. Well, if evolution is a guiding principle of historical study, and by some historians it is, and by other historians it isn't, but if we do consider it as such, then, of course, in that sense, evolution of a community is a perfectly normal historical process. Can be spoken of then either as a progressive change of community with time, or it can be spoken of as a development of community without giving directional aspect to it. But the question is there anything more in evolution of a community than this? Is there community evolution? Well, I've kicked this around with a lot of my friends. A lot of us have. It's a very difficult thing to think of. You can, however, draw some analogy to organic evolution, as long as you don't start to put the mechanism in. Sure, the community may have duration over time of a long period. It may not change in structure over time. On the other hand, it may split into two types of communities. It may, so to speak, have a speciation. If you don't get the motives involved as the same one, it does do this. It may become extinct. Or it may not split, but become so altered over time that it's a quite different thing. All of these things can happen. Can we have hybridization of communities? Oh, yes, of course. I think that's stretching it pretty far. The only point is that it's within this frame of reference, the moving through time in a progressive fashion, with tremendous stability, provides a framework in which we can then look at the phyla going through time and make sense of them. And that is the whole object of this, is to make sense of the things that are observed in the phyletic studies by putting them in a much broader context. Now, how successful is this? Well, I'd like to spend most of the time that I have on communities telling you about them, to talk about the one I know best, and that is the community which exists in reality, existed in reality, in the Texas and Oklahoma Permian, and also in over in Dr. Vaughn's Permian to the west and so forth. But the Texas and Texas and Oklahoma mines, we'll talk about that mainly. It exists there. It was a community of this general sort. First, the vertebrates. It included a great many fish. It included among the fish a vast number of sharks. Remember, these are freshwater. All of them were predaceous. It included among the fish a great many lungfish. Some were estivators. What they ate, I'm not sure, but it pretty clearly wasn't plants. They ate probably invertebrates. They may have grubbed on plants somewhat, but probably their diet wasn't too different from that of many modern lungfish. It consisted of cross-opterygian fish, the lobe fins, highly developed predators, and probably the idea is getting across even in the fish, and a great variety of paleoniscoid fish, little fellows so long, big ones this long, deep-bodied ones, and so forth, most at least of which fed probably on invertebrates, on each other when the opportunity provided itself, or on anything, but in general were largely not vegetation feeders. This is what we see in the fish. They live in the water, obviously, not associated with the other animals directly, but I try to pull them together. The amphibians were in great array, all sorts, types, sizes. Biggest ones like Ariops, if you know the name, 8 feet long in some cases. Big semi-aquatic predators. Smaller amphibians, an aquatic one, Trimereratris, it's a fish eater, probably, definitely a predator. Getting down the line, we come to some smaller things. There's an estivating burrower called Lysirophus. I don't know just what he ate. He probably ate small fish and such. I found coprolites that presumably belonged to Lysirophus that had paleonism with scales in them. So this seems reasonable. We find Diplocaulus, this fantastic thing with the peculiar pseudo-horns on his skull, and he probably grubbed around the mud and ate anything that came his way. Vegetation, little invertebrates, probably mostly that. And I can go on naming a lot of amphibians, but the point is, I won't name any more. Almost all of them were not plant feeders, but they ate other animal life. Come over to the reptiles, and this is in the community. We had, of course, this thing I showed you here, Sphenacodon, Dimetrodon, very much like him. Big predators. They ran up to 12, 15 feet in length in some cases. Well, 15 is a little long, 12 feet, good enough as far as they go. There were some herbivores here. There was the Apatosaurus that probably ate plants, semi-aquatic form, but extremely rare. There are very few of them. We have in this fauna also Diadectes, and I don't know what he ate. Maybe he ate seeds off of plants or something of the sort, or maybe even crushed shellfish, as some people would like to suggest. I just don't know. He's an odd one. But again, he's a rare thing. We don't find much of him. Among the reptiles, then, we also have the Captorhinomorphs. Some of them definitely were insect feeders, predators of that sort. Some may have done some plant feeding. The problem here, as so often in feeding, is we just don't know what kind of food these things had unless we have a modern analogy to take with it, and we don't have any modern analogs of the Captorhinomorphs in terms of dentition or habits. But whatever you come up with, if you take a sort of a field of biomass of the vertebrates, you run into a rather embarrassing situation that about 95 or 90% of it was predaceous. And this is a losing game, because they're obviously going to eat themselves up very shortly. They didn't. Well, now, the two answers, well, there are probably a lot of answers, but there are two answers to this. And some of these, of course, come if you take a look at the plants and invertebrates. What were there? Well, the plants were essentially a coal, measures flora, sorted out with a few types. There were ferns, there were scale trees, lots of equisetum, or equisitales rather, many times conifers, which were not much the coal measure type of thing, but they came in a little later. In other words, it was this type of vegetation. And actually, when you take a look at it, you find it rather hard pressed to find anything very nourishing for a small vertebrate to go around feeding upon. Maybe they did. They could have. It seems like they must have been adapted to a fairly harsh diet. If they did, there's no evidence in the ones we know that more than a few of them ever made it this way. Invertebrates, well, the record is pretty terrible, right where the vertebrates occur. Oh, you find a few pelecypods, find where a skinnering-type critter ran across the sands once in a while. What he was, I don't know, but he had many legs. This sort of thing. This is the sort of evidence you get. Oh, we find ostracods once in a while. But not far off, we find tremendous numbers of insects. Now, we don't get them right where the vertebrates are in Texas. Within 20 feet vertically in Oklahoma, we do get them. Lots of insects. Insects almost certainly were a very important element. Well, now, if you look at this whole picture, something is very, very wrong in this whole setup. And as I said, there are two possible ways of answering. One is our sample is just terrible. Our sample is so bad that we can't rely on it at all. The other is that the sample isn't that bad, and we have to reorient our thinking from at least what mine was. Maybe yours hasn't been. You probably haven't thought about it much at all. But if you have, perhaps you would have thought like I did, that we would look at this in the frame of reference which we see in a modern community of mammals, say, where there's a tremendous number of herbivores and a small number of carnivores. The carnivores feed upon the herbivores, and the herbivores feed upon the plants, and all goes on happily. But this couldn't have been the case, unless the sample is terribly off. And I just don't believe that's far off. We take samples, for example, just grab around, we'll find that in the average sample, Dimetrodon, this big predator, runs numerically anywhere from 45 to 75% of the animals that you can identify. Now, there's tremendous bias in this, because Dimetrodon's big, he's easy to identify. One Dimetrodon falling down and floating apart can make a lot of specimens. He has long spines, they break up, you can recognize each piece of them. But still, it isn't that bad. If it was only 10%, we're still in trouble, and yet it's 45 to 75%. Well, we of course have close by here Rancho La Brea, which has a similar situation, but that is rationally explained, I think, on another basis. Well, as a result of all this sort of thing, this deltaic fauna that we're dealing with, looked at from a community point of view, appears to be one which had a completely different food chain setup. Now, I published a paper some time back, which I sent out here, some of you may have seen, on food chains and the origin of mammals, and this is what I'm talking about. This was based, apparently, in an aquatic zone as far as getting inorganic material into the flora was concerned. The flora was, by this I'm not expecting this alcohol at all. The flora upon which the animals fed was aquatic. Therefore, the transfer of the inorganic material to organic, the inorganic input, was basically aquatic. Going through the invertebrates, going through the fish, the amphibians, and reptiles, the reptiles being almost entirely fish feeders or feeding upon each other. Well, how do we know they did this? Well, we've got coprolites to go on. And how do we know the coprolites go with particular animals? Well, there's one good way of judging in one case, and that is Dimetrodon is the only big enough carnivore there to produce the coprolites we get. What did he eat? Well, Peter Vaughn maybe could tell you more than I can, but I know some things he ate. He ate Dimetrodon, he ate Ariops, he ate Diplocalus, he ate Paleonestoids. He didn't eat sharks as far as I know, but maybe he did. But we find these in the coprolites. So, you see, we get this beginning of picture of predator on predator, the whole thing going back. Well, that's interesting, so what? Well, the so what of it is the implications. That is, the implications as to the evolution which produced mammals. I think it's extremely important. We have a tie, then, of this particular faunal type, this particular community type, to water. As long as he maintains his structure, he can't get away. He must have his feeding back in the water. Sure, there are animals on land, but they're feeding in the water. If they're feeding in the water, and these big fellows are fish feeders, the principal objection people have raised time and again is, but are they agile enough? This is lovely if somebody brings this up, because this is precisely what evolution towards mammals has been. It's towards agility. It's towards three-dimensional agility. So, there are lots of interesting things when you look at it this way. I mentioned the amphibious nature of mammals. I don't think I need to explain that. Fits the pattern. We mentioned many other things I mentioned. Another thing that has to come out of this, and fits in with this faunal picture as well, with agility, then you can see mammals coming to be. But a thing that's very bothersome is that although we do have these agile animals, these mammalian characters keep coming in, and things that go off adaptively in this direction into a slugging existence, they still get more mammal-like. Hence, in this full array, and I think in the aquatic setup it's partially explainable, we seem to have some key change, some key innovation coming in, to which other changes were then later adapted. Well, this perhaps not, but it's a possibility, was the development of incipient warm-bloodedness at this stage, or at a stage a little later than this. Now, this can be argued and fought, and it has been argued and fought. Well, this community I'm speaking of here, which I've given you some detail on, persisted from at least the beginning of the Permian on up, and is still picked up in the Soviet Union up near the top of the Permian. It's a very persistent thing. It's what I'm calling type 1 in the slide that will come up in a few moments. There are two other communities that are pertinent to our consideration here. Now, there were lots of others existing, of course, in the ocean. Maybe others on land, we don't know of them if there were, but one perhaps is there. Number 2, I would call the mammal type. That's what I'm calling. This is the one where we have the balanced mammalian food system where plants are eaten by the mammals, the large herbivores, the carnivores feed upon them. Insects, of course, enter into the picture, but they enter into the picture in a rather minor way. And then the third type is a rather difficult one. It is an insect-based, terrestrial community, and I'll bring that up in a minute. But the important thing is that this seems to be that type, basically. Some of the Captorimnors. Now, perhaps in a later radiation they deserted this, but in an earlier part, they seem to represent a group which got into land and could persist on land and operate on land because they were divorced from water into the food sources of insects. Well, now if we can turn over the slides, I'll develop this a little further in terms of those, the next slides. These slides, the last slide, I'm sorry to say, is not as good a one as I would like, for the reason that I somehow or other in the course of shipping, one of my figures got lost, and it's an older figure, which was when I didn't know what a community was, that I sent in and then changed. This is a slide of the type 1 community to show you the basic pattern that I'm thinking of. Inorganic input through aquatic plants, leading to aquatic vertebrates, that's some of the fish and amphibians, to aquatic invertebrates, various ones, fed upon by the aquatic invertebrates, and these leading basically to terrestrial and semi-terrestrial vertebrates, mainly fish and amphibian feeders. And when there's an arrow like this, it means they were feeding on themselves, on each other, so to speak, which of course happens. And a very minor input to terrestrial plants, and a few terrestrial invertebrates leading in here, and a very few terrestrial vertebrates. That is the basic structure. Now that's oversimplified, and to show you more what a simple, still simple, but nevertheless more complex picture would look like, may we have the next slide, please. I don't expect you to follow this. There are some mistakes on it, but I won't point it out. The pattern is an attempt to take aquatic, semi-aquatic, mostly terrestrial, which is a good definite term, and terrestrial, and try to see who ate whom, indicated by the arrows, and how this whole thing might have interacted, interoperated. Now, this is obviously ambitious. This is obviously partially fictitious. Yet, an awful lot of it is probably not too far off. But you'll notice how it all bases down into here. You'll notice if you get a thing such as Dimetrodon, that he was happy in eating most anybody that came along. Interesting thing there, Dimetrodon did not change materially over the whole period of Lower Permian. He stayed about the same. Well, community evolution suggests a reason. He was ubiquitous with reference to his food supply. Came out of the water one way or another. Others that were much less so changed more. Arias, very persistent, same thing. This similarly, and so forth on down the line. Well, this is the sort of picture you might construct. I think I could do other ones, but this is the type 1 community blown up. But the next page. This is the type 2 community that we have here, running across. the mammal type, and this is where this all was going to. We'll see this occur from time to time. The input, as I mentioned, in terrestrial plants, mostly terrestrial herbivores, fed upon by terrestrial carnivores, a slight dip through the invertebrate line. The next phase, this is the number 3. This is a strange one. Yet I think there are examples of it that can be worked out. Inorganic input through a terrestrial plants fed upon by terrestrial invertebrates, largely insects, fed upon by terrestrial vertebrates, largely but not entirely. Captorina, some amphibians involved in there, and a slight input through this other direction. This is the type of community which is extremely important in this story because it appeared and then almost completely disappeared. But my guess is that it is the community from which came the other big radiation, that is of the Lepidosaurid, Archosaur reptilian radiation, which became terrestrial and largely disappeared from sight for a long time. Now may we have the next slide, please. Now this is the last one, and this is the one which will give the picture as I see it somewhat, although not as well defined as the other slide I would have, had not my picture got lost somewhere. This is the number 1 faunal type that I spoke of particularly. Now the striking thing throughout here, and the thing I want to emphasize, is put this in a sort of a teleological sense. Time and again, these things tried to develop a good terrestrial type 2 community, and time and again they failed. This is one in Oklahoma and in Texas, a type 2 based upon a very big herbivore known as Catodorhynchus and also something called Ankylosaurus, friends and relatives of this sort, which is the first pulsation into a type 2 community that we find. Very early. Came off of this, went on. But it failed as far as we know. It went out completely. We picked this up in Russia, incidentally, also. Then we come over to a 1 or 2 here. Now that can be taken out. That was 1 definitely from Yeshevo complex in Russia, which is very comparable. This type 1 aquatic going on at the Bashkirian complex in Russia gives another of this. The Kargalian complex in Russia gives another one. And finally, Yeshevo is the last I know in the record of this. But notice the persistence of this aquatic type. This is the one through which the carnivores that produced mammals came. Off to the side here, coming up rather vaguely and disappearing, is this type 3, which I've run off into here. At Shikovo-Cherky, in Belibai and Mazan in USSR, we have actual examples of this thing. We probably have down in here, but I find basically as a part of this community down here, which pulled off and separated. And I presume that up in here it gave rise to the Lepidosaurid-Archosaur complex. And that is a very sketchy, touchy one, which I'll only say is subject to many interpretations, but this is as good a one as I know. Well, the next push off into a type 2 was a Paleosaur complex. This is a great, big, clumsy outfit that probably came off of here. Heavy-boned, abundant herbivore that was interacting with a complex that came up in here. First with carnivores feeding upon pariasaurs, and then going on to here, and then gradual change, tying in with one which is another push, in which the anomodonts, I can't see what I'm playing here, anomodonts came in this particular case. There is then, those are Dicynodonts, but there is then a third push. 1 on the land, 2 on the land, 3 on the land. It went out. This went out. This went out. At this time then, we see continuing development, and a few of the anomodonts lasted over. But up in here we come into a completely different one. Here we have an herbivore coming from a carnivore, a Gomphodon cynodont type complex, where once again we get the type 2 community. In other words, that is a fourth example. These things come and go, and this should have succeeded. It was a dandy. Everything was in balance. Apparently it looked great. Good carnivores, good herbivores. Everything was going fine. The fact of the matter is it didn't. It became extinct and left as remnants only these little mammal-like creatures up in here. What happened? Well, what I think happened, and now there are those that argue with this, is that developing as a real terrestrial fauna faunal complex community over here, the Lepidosaurid-Archosaur type, now some of them occurred in there, but not many of them, These came into contact as it became highly terrestrial. And in the competition, apparently, these couldn't make it. That's putting it very briefly, but the time is very short, and it would take a long time to explain it further. Fact is that we have an aquatic-based community coming onto land a number of times, getting a well-balanced situation here. However, a much better established terrestrial community with a long history meets it. Competition is one that most of these animals go, not all of them. Here we start then with a few little mammal-like creatures that go on. Are they mammals? Are they not? I don't know. They are very mammal-like. They persisted throughout a long period of time, up to the Upper Cretaceous essentially, and then, I can't read that up there, but let's say it goes up the Upper Cretaceous. Then at this point, in came the big radiation, the big push. Well, what was going on all this time? Well, it's been said they couldn't go because of the reptiles. I think this is dubious. I would give a guess that what had happened there was that these were still not particularly highly mammalian in many of their fundamental characteristics, and that this whole period was one of gestation, but as a part of the reptile community. And finally, when whatever happened to get rid of the reptiles, and I certainly don't know what did, these were at the threshold and were able then to once more burst forth as mammals to produce much the same sort of thing that as almost mammals had produced here. Well, this is then a phylogeny of communities which is extremely instructive, and if you think back to the many things that I pointed out in the phyletic aspect and the things that we need to explain, this is a mechanism, this is a model which, taken evolutionary theory as we know it, adequately explains all that we see in the record. This, I think, is about all that you can expect of a hypothesis. And this is the hypothesis couched in community terms that I present to you. I understand tonight I will be subject to all sorts of searching analysis of this, but the more I say, the more I can be searched, so I think perhaps at this point I'll leave that picture with you. So thank you very much.
Dr. Olson is available to even answer some questions here this afternoon. Who will be the first? Well, if no one else has a question, I have one. In that slide you showed early in the game where you were showing the dentitions of some of these therapsids, you referred to certain ones as being meat eaters and others as being vegetable eaters. And I couldn't see very much difference in the dentitions as they were showed there. What differences in dentition go along with these feeding habits?
Well, there are a number of features in here which are really difficult for this reason that it is difficult on the basis of dentition alone to know that a thing's an herbivore or a carnivore. Anybody who has a cat that eats grass and carrots knows the problem. Or this sort of thing, and the dogs eat games, meal. This is absurd. But animals will eat anything they can get. What I mean when I say herbivore is that this was dominant. Now the dominant herbivore must have, one who's dominantly herbivorous must have some mechanism for getting the food prepared and for swallowing it. Now there's a number of ways of doing this. One is to grind it up. Now as long as this goes on, we've got good evidence. One that you saw on here which had no teeth at all except for a couple of spikes is in good shape because he had a turtle-like beak and hard plates. Nobody ever saw them, but we know they were there. Which were used for grinding food. This is a dicynamide. This is not a problem. Another one I didn't point out, but you may have seen a terrible looking thing staring out at you down in the lower right-hand corner to you. This I would call an herbivore. Well, this is the most amazing looking creature you ever saw. What kind of teeth has he got? He has a tooth.
That one was one that I was particularly worried
about. Well,
about.
this is a thing that no rational evolutionary theory can explain. It's why a thing like that should ever come along. But there he was. Well, this has a tooth. If I look at it, a lower tooth, which has this crown pattern. Jaw come along there. Now he has a whole bevy of these, and then up front he's got something else. Serial long teeth. For again, for many lines of evidence, this type of tooth is the type of tooth that commonly develops in herbivorous reptiles. Now, can I base that on the tooth alone? No, not on the tooth, but on all of the other features of the animal that strongly indicate it to have been an herbivore, not a predator. For instance, in Caseids, we have, if I may draw a picture of this, they have that type of tooth. We have an animal, some such proportions as this, and he has a head like that. He has big feet, padding feet. On the palate, he has teeth, many teeth, not for grinding, but teeth which clearly aid in mobility of the skull and the vegetative back. This has that kind of tooth. The pariasaurs, which stand about this high and are absolutely totally clumsy animals, a femur this long is this wide, were not carnivores, I think. They couldn't have caught anything. Furthermore, they have this kind of tooth. This repeats over and over and over again, whereby you begun to think that when you get this sort of tooth, maybe you're dealing with an herbivore. Brontosaurus, Diplodocus, and all their friends and relatives with skeleton had that kind of teeth. This is again this mass of putting together all sorts of bits of it, but you arrive at this as now other things happen as well. The jaw structures are more massive, they're less tendency to reduce the dentary bone. The jaw musculature, which I don't want to get into, does not modify as much. The palatal teeth are often on in great masses for holding. The jaw action is very rarely one in which there's any lateral swing at all, but it's totally up and down. But there is almost always maintained a mobility of palate structure for using the palatal bones to get teeth back until secondary palates come in. All of these things come in. So it isn't teeth alone, but it is once recognized the types of teeth. If everything else looks like it, then it looks like it's a good type of teeth.
What did the dentition of the insect eaters look like?
Of two general types, but if I can draw, I'll have to put the jaw on here. That sort of thing. In other words, a simple cone type of tooth with some accentuation in the dentary region, in the region of the premaxillary and canine area, and sharp palatal teeth turned back in some of them. Now, these captorinomorphs I speak of, if you look at the lower jaw of some of them, these are not the kind I refer to as necessarily predaceous, have two big teeth, a couple more teeth, then they go into multiple rows. Now, if you look at the front teeth in the skull, they're long, hooked teeth of this sort. And there we have some precedent. There are long hooked teeth on many animals that do the insects, particularly when the mammals do this. So this is a fossil. This is what they look like. Now, when these things got farther along, I'm not sure if they kept on eating insects or not. This is the basic stock. Everything they've done is herbivore. They do this. But this is the pattern. Now, when we get into strict carnivore, then this apparatus becomes very much longer, well developed, a couple of canine teeth, whoops, and we begin to get cuspidation on the teeth of various sorts. And the teeth, looked at laterally, become very good, sharp, shivering, cutting type teeth. And these are different. But these are tooth differentiations, but you cannot use the teeth alone. You've got to take the whole thing into consideration. And as I say, animals are awfully unpicky about what they eat when it's hard to get something. Horned toads, for example, all of you know horned toads will eat anything they can get if the fly jumps or hops. But if there are ants around, they'll eat ants. Outside of that, they'll eat flies, moths, beetles, anything else they can get a hold of. But mostly sampled, they eat ants. So this is a problem diet.
I can see how the earliest late Permian type 1 community of Russia was not in contact with the earliest late Permian type 2 community of Texas. But given a couple of million years there, and assuming that evolution was roughly similar in Russia to that in North America, would you have expected these two kinds of communities to come together? Wouldn't this automatically almost produce a type 2 complex?
Now, let me get all the ones you speak
Well,
about.
how would you maintain the spatial separation of type 1 and type 2 communities in the earliest late Permian there?
I don't think it should do. I don't, this is not, this, well, let me dive in. This would be oddly crude, but this I think illustrates. Let's say that this is a deltaic area coming down in here, and we have a river coming down this tributary system down in here. Now, this type 1 community is inevitably bound, according to my thinking, to this sort of a zone. In other words, it's got to be around water and it's got the base in there. Evolving a type 2 community, if it evolved from here, now allows it to exist separately in that sense. And this would be a potential isolation of them. This apparently is exactly the thing that happens as we find them. We get this type of community separated. Now, this does not mean that there isn't overlap and interplay, obviously, because these aren't that discrete. But this has then the potential of existing independent of water. This cannot. And this is the difference as I see it. It doesn't mean this is not in areas where streams are, but it can exist without food dependency, whereas this one cannot. At least that's the proposition I would make here. And I think if it can exist, it will exploit areas which the other cannot exploit. And it probably came to be and developed enough. You know the situation of the casids, and I think you do know the situation of casids. Casids, most of you probably don't. Casids were the first animals that made this break, as far as I could see, from water as such. Catylorhynchus, I mentioned, this critter I tried to draw here, which runs about 15, 16 feet long, incidentally, was one of these. Cassia, there are 3 species, there are a whole bunch of these things. Well, now we get a most peculiar situation, which I think is indicative of this. In the whole Texas collecting that I have done, and others have done, there are 3 spots in the lower Permian that cassia occurs, and only 3. I mean spots like this. That's all, there is no more. I think, without any question, we're tapping the beginning of this type 2 community that appears so full-blown up in Oklahoma, which existed in the area, but existed ecologically somewhat separate, and only on occasion fed into this complex and finally they're erratic within the complex. There are 3 cases that are found, interestingly enough, where this is found in Texas. 2 other types are found which are repeated with it higher up the series, which is very peculiar and interesting, and meaningful, I think. So these are the sorts of things. Now, I think you know what I'm talking about. I don't know if the others do or not, because Pete happened to work in this area very closely. And there is this repetition here, and then we get the full-blown community. And what I'm trying to say is that it would be much as if we were sampling, if this is a cliff in here, say, a community down in here, and occasionally from up in an uplands here, one of these came down and got preserved. Well, these can be ecologically very different, upland, lowland, even though they're a mile apart. And occasionally, an animal from here may get down in here and be preserved. And this is the type of thing I'm looking at. I think the picture is simply this. Always remembering there's a terrible sampling problem.
Assuming that animals that eat animals that live in the water are different than those that will eat little animals that live on the ground, and then those bigger animals that eat the water eating, or water life eating. Would you then venture to say possibly that the final success of the type 2 community was correlated perhaps with the new type of job that was involved?
Yes. I think this is undoubtedly, is definitely involved in this, because a thing I didn't say, the thing I should say is this, that all of this there are many thresholds involved in here, and until certain patterns can be developed, the occupancy of a particular ecological niche, I hate to use it too restrictive, but ecological zone is impossible. Now, the ultimate success in the Gonfidon group that I pointed out, and it was very successful, tied in, I think, with the fact that it had a particularly well-developed type of jaw musculature, which I won't try to indicate, but basically, if the skull is here, what happened here is the jaw musculature got a much better pattern of this sort, and the dentary was almost complete in here, excellent. These had grinding dentitions. This was an extremely successful herbivore, which could cope nicely with all sorts of kinds of vegetation, whereas the early ones probably couldn't. I don't know what these early fellows ate, as a matter of fact. I suggested to a paleobotanist friend of mine that they probably ate some sort of tubers underground, and such as what tubers? Well, I don't know. Can't you supply me some? He said, well, I can't think of any. That's too bad. Maybe they ate ferns. Ferns just don't, well, to me, they don't appeal. Maybe. I can't quite see an animal of this sort eating ferns, or maybe dead. But these were able to cope with many types of food situations. I would say that, yes, much in the total skull structure, the jaw musculature, the structure of the jaw, the structure of the teeth, made this great success then possible. Whereas the earlier ones just didn't quite make it, and probably could not compete well with any minor changes. One foodstuff goes, they go. Mm-hmm.
Yes, the evolution of the carnivorous mammal reptiles to the mammals was controlled by the evolution of the herbivorous mammal.
Yeah, partly. Mm-hmm. Yes, I would say through this sequence that some of the developments in these, particularly those which freed carnivores from this aquatic tie, correlated and could not have taken place had not some of the other members, some of the herbivores, come to be so they could exist with them. This produced then a somewhat more advanced, rapid-moving carnivore. However, this went on sporadically up and up the time until we got this balanced fauna, which was a beautiful one, where there was this nice dependency between the two, and they all went to pieces. They didn't last at all, except for some very tiny ones. Mm-hmm.
What size were these herbivores?
Most of them were big. The herbivores in the lower Permian, I mentioned the Dilophosaurus, was an animal that ran about 8 or 9 feet long usually, and without his back spines would have stood about this high, something like, might run, say, 75 pounds, 100 pounds, something of that sort. The Catylorhynchus, this fellow, I have examples of them up to 20 feet long. They stood about 3 feet high. They had extremely massive ribs, so that the body cavity was very large, very flat, something like this. And I would hate to venture the weight on these things.
How about some nice small herbivores for some of the small predators to feed on, rather than insects alone?
In the early time, I don't find them. There's no evidence of them. Later on, higher up, yes. Some of the Dicynodonts, the Nomodonts, are nice small ones. At that time, we have small carnivores, which, however, were not fish feeders, quite clearly, but were undoubtedly feeding on these. There is evidence of this. But in the early stages, no, there is nothing of that sort. The small things that are being fed upon by the reptiles, which were herbivores at all, were some aquatic amphibians. Of course, this is where you tend to stay with classes. Reptiles have to eat reptiles, amphibians. And of course, it doesn't work like this at all. Reptiles do eat amphibians, and they eat lots of amphibians. This was a principal source of food for them, undoubtedly, because the coprolite pattern is one that we find a tremendous amount of amphibian material, as well as fish and other reptiles. I got on first, I really actually coprolites are what started me into this. I was working over at the museum in Moscow on some amphibian coprolites, and they were beautifully preserved, and I began to try to find out what was in them. And I found, first of all, that his own species was there. Secondly, that he was eating cross-opterygian fish. Third, that he picked up a carnivorous reptile along the way and eaten him. And anything he'd find in fauna, this fellow's been eating. So that this what sort of keyed this off. And what is an interesting information. Maybe they can eat themselves and still persist. And this is where it all started. But there are none, to go back, in the early time, outside of these very small numbers, there are no adequate small herbivores. No. How good the sample was. I can't answer this. I am fairly happy with the sample from the Texas Permian arroyo, because I've collected it a lot, I know a lot about it, I can go in and looking at a particular type of deposit say these generally will be present. Usually they are, sometimes they fool you a bit. And we do not get new animals, we repeat and repeat and repeat in terms of numbers, in terms of kinds. I think this is pretty good. When we get up in some of these higher things, in this country the sampling is bad. When we get into Africa, apparently it's very good, but I have not had the good fortune to work in Africa, to South Africa, where there are the finest Permian and Triassic deposits in the world, so all I know is what I have read, and until very recently they have not even thought in ecological terms or collected in ecological terms. A crowd or a ranch, say, of 100 to 200,000 acres collected will be in the literature as these occur together. Well, what does that mean? You don't know what it means. To occur together, they've got to be in the same formation, in the same stratum, in the same place, right here and now. Whether if they're 50 miles apart, maybe 100 feet apart stratigraphically, this is the sort of thing you can't go. And now recently they've been doing good work over there of this sort, and it's going to help a lot. Now, I'll let you.
We'll take the man in the yellow shirt, he had his hand up first. And then Jan Phillips, and then the gent with the beard, and then I think we better let you go.
Going all the way back to your fish-based community, you said there was a predominance of predators there also. And
Yes.
Then how are you moving the inorganic material into this biome?
Mainly through invertebrates and to some extent through fish.
Have you got any record of the invertebrates that are doing this movement?
To some degree we have it. Unfortunately, as perhaps you know, freshwater invertebrates tend not to preserve well. It is unusual to find in the deposits where the vertebrates are themselves specifically more than scant evidence of this. In adjacent rocks in which invertebrates do preserve well, in special cases, yes, we have very adequate invertebrates. One is the gastropods, pelecypods, various types of arthropods, small ones, and of course there's a great many insects. There's a tremendous larval component here, and so forth. But these do not generally come right where the vertebrates do.
If you find mollusks and arthropods, your fish are basically unsuited to be eating these.
Not all of them.
You're basing this all on a few fish capable of eating arthropods and mollusks?
No, not entirely. I am basing it upon the fish and the amphibians and some of the reptiles as feeding upon these invertebrates. It is not that all predators, all the amphibian predators, for example, were feeding upon fish alone. There are, I mentioned Digitized, for example. This clearly was a plant invertebrate feeder. I mentioned lungfish. They were probably invertebrate feeders very largely. They may have fed on plants a little. This type of thing is where the transfer took place. Diplocaulus was one of the primary sources of food among hard-bodied animals of Dimetrodon, which is pelycosaur. Now, he also ate fish, we know, because we find the fish scales as coprolates. But he certainly was not a clam eater. But there were other things around which were perfectly capable of.
You seem to throw out that your sample is notoriously bad for the evolution in the field, but there exists the possibility that because you don't find the invertebrates that would be doing the transferring, that they don't in fact exist, whether they would have preserved or not.
I think after we've had your rejoinder to this, we'll go to Jan Phillips.
Well, all I can say is that within reasonable distance, under reasonably similar circumstances, but under different sedimentological conditions, where these particular types of invertebrates do preserve, they're present. But in the types of beds that we find vertebrates, the preservation generally is not that in which invertebrates tend to preserve. They need extremely fine-grained sediments. They need extremely quiet conditions. Mainly, we don't get those. Now, they do come in there. We get them, but they're rare. The aragonite shells such as these have do not stay very well, and insects are, of course, extremely special. But in Kansas and Oklahoma, in the same types of beds, but in slightly different facies, there are adequate invertebrates to supply anything of this sort. They are there. But they aren't right for the vertebrates. I wish they were, but they aren't. And as you say, the thing may be totally biased. I don't think so.
Your turn, Jan.
I wonder what kind of insects were eaten and the size of the animals they ate.
Well, the insects that are in there are of various sizes. They are, there's a very highly varied array of insects. The biggest ones running up to about like this, and all manner of small insects were in there. In addition, there were various other things. Now, what kind of animals ate them? The insect feeders, as I would see, that we're dealing with are generally animals, running up to a foot and a half length, something of that sort. No big ones. But there is a very good insect fauna in here. I can't run down name the types for them. Carpenter's done the work on it. From Oklahoma, Sellards, and later Tilliard did work on the Kansas ones and such. They're available. But it's a good one. It's a good one. But there's generally small insects and small predators eating them, or insect feeders eating them, I think.
Professor Olson, it's always surprised me that with the amphibians who have spent so many million years going to so much trouble to become terrestrial, the last fossil one to get up in the tribes and things, the plesiosaurs, you mentioned Dromaeosaurs, show definite signs of secondary aquatic adaptation. Did they like that thing? And also, or wouldn't you go, don't you go
No.
with this idea?
I don't think the majority of amphibians ever got terrestrial.
No,
There are a few that did, but the great majority did not. In the very earliest part of their history, the ones we know best are aquatic. Most of them remain essentially aquatic. There are a few cases among such things as a group known as the Dicerophids, which did become terrestrial, I think quite highly terrestrial. As today we have, for example, some of the groups among the Anurans are highly terrestrial, but basically they never did.
What about the Areopsids and the Adopsids and things like that?
Ariops certainly could get around on land, but Ariops seems to have spent most of his time in a rather alligator crocodile-like fashion, lying around snapping at whoever came by. The same for the Adopsids, I should say. I think now the general consensus is that amphibians really never did become terrestrial, because those that did become terrestrial were on the stock that was reptilian-oriented and became reptiles. This old idea, and we always had it, that the amphibians made a grand play on the land and got chased back in the reptiles, I think it's fairly naive. Most of them didn't.
I was wondering in terms of whether your idea of this food chain, that these other forms and maybe the ancestors of the modern bliss activity, which obviously have been in the water for a long time,
Yes.
they sort of got fed up with the jam, the struggle of living, having this quasi
Gave up.
food train, and
Yeah.
decided to go the whole hog and go back again. I just wonder how you felt about this. Hey, helps. Somebody ought to come up with some idea as to why we, the only amphibians that we're left with seem to have given up living on land altogether, except the ones that have now.
Later on came on a minute. Well, I don't think they really did give up living on land. I don't think they got to living on land. I don't think it was that. I think these things have been very largely aquatic throughout. And almost all the ones we find, you keep finding these, well, he could have gotten land, but it looks like he's aquatic. I can just tab down the list until we take the Dicerophids and perhaps the Trematopsids. Those two, somewhat, yes. But the assemblages you find those in are not basically terrestrial assemblages. You do not find them with the Dimethrodon, Captorinus type of thing that did live marginal, but somewhat on what I call the upland, if there is any upland in this. You find them with Simoria, Trimerarachus, Susharks, and so forth. This is their bailiwick assemblages. Simoria and Dicerophids and Trematopsids are very common substances. This is a thing I didn't mention because the time is much too short. A great deal can be done by repeated assemblages in the field that you get over and over, and this is predictable. Knowing the type of deposit without visiting it, I can predict about 80 to 85% of the time the assemblage that you'll get there, and I'm sure people do the same thing. When you know a place well enough, you've got to really have walked it till you've just about died walking it, but you can do it. It is possible, and this I think is important. So I don't think they ever did make it.
I think we have time for one more question from the lady over here.
You might have said this before, but you were saying that it seemed that the development of the Thoraxid through the major part of the grade towards the mammalian grade occurred in this second type community which did not persist outside the Mesozoic.
What I tried to say, and I may not have been clear, was that the early part of the Paleozoic history and the very early part of the Thoracic history was bound to water, was in the type 1 community. That repeatedly, and we know of about 5 cases, an herbivore component developed with sufficient biomass of speak that it could support carnivores. That this repeatedly went out until we get very well up in the Thoracic history. Then we get the terrestrial herbivorous community that persists coming from these therapsids, and that this went on through time very successfully, and that the major transition towards really mammalian conditions, that is where they got 90-95%, took place in this, and that is a time of very rapid change. And then from that, weeded out the mammals. That's what I tried to say. I'm not sure if I was clear.
Yeah.
Mm-hmm.
Thank you very much, Ollie.